Hello, my name is Tripti Mathur. I am a graduate student at San Jose State University studying electrical engineering. My term project for EE 275 Advanced Computer Architecture was to build a NIOS 2 instruction subset architecture. This project was undertaken in summer 2016 under the guidance of Dr. Chang Chu. This slide shows the topics that I am going to talk about in this video. We are going to start with an introduction, continue to the design and implementation, look at the verification, conclusion, and future scope. The introduction is about Altera's soft processor called NIOS 2. This means that this processor is implemented on an FPGA. It was developed by Altera. NIOS 2 is a reduced instruction set computer architecture that is a RISC architecture. This means that fewer instructions are needed to accomplish any task. Harvard architecture means that there were separate storage and signal pathways for data. Registers structure in NIOS 2. There are two types of registers. The general purpose registers are used for arithmetic and logic operations. Data is moved between them using load and store instructions. Control registers have special meaning. The assembler recognizes them as control registers. There are 32-bit general purpose registers, and some of them have special meanings as seen in the uh, slide here. The control registers, there are 6 in number, and these are also 32-bit registers. These also have special meanings which are seen on the slide here. The basic block diagram of the NIOS 2 processor is seen in this figure. As we see, there is an arithmetic and logic unit. There are cache memories for instructions and data, general purpose and control registers as described previously. There is also program controller, address generator block, and controllers for exception and interrupt handling. There are three types of instructions that NIOS 2 can handle. First one is called the I type or the immediate type, which example are arithmetic and logic instructions like add I and I, branching instructions, and load and store instructions. R type instructions examples are ALU type, which are add and NOR, comparison instructions like CMP-EQ and CMP-LT. Custom instructions are also R type. The third type is called jump instructions, call JMPI. They transfer execution anywhere between 256 MB range. This is the 5-stage MIPS pipeline. Basically, a pipeline architecture helps to increase the throughput and speed up the working of any processor. There are 5 stages in any pipeline in this particular project. The first step is called the fetch stage. In this, the program counter, which points to a location where instructions are held, when the PC is modified based on which instruction is called. The decode stage, instructions are fetched and broken into opcode, data fields, and interpreted offsets are also calculated. In the execute stage, generates of the branch address, data memory address, results, and write back register address. The ALU can perform addition, subtraction, multiplication, comparison, and logical OR. Fourth stage is the memory. The fourth stage is the memory access stage. Read and write operations are controlled in this stage. In the write back stage, the address of the register where the data is to be written and branching addresses are generated for R type instructions. The major problem of these pipelines is something called hazards. These hazards reduce speed up and performance. Three types of hazards exist: data, structural, and control. The simple solution to avoiding hazards is to stall the pipeline. This stalling of the pipeline is done by introducing bubbles or periods of no operation. Verification of this project was done using three different programs. It was carried out using Synopsys tool called VCS, and simulation results are viewed using GTK Wave. The first program was to find the sum of the elements of an array. The array was a test vector which contains the digits of my student ID. The number is found to be, the sum of these digits is found to be 20 in hexadecimal, and the program is now optimized. The program is visible in this screen here. The verification of the sum of array program is seen here. This is the waveform. R3 is the register which contains the digits of my student ID, and the result of the addition is seen in register R2 as indicated in the waveform. The second program that is used to implement and to verify the working of the project is is to find the dot product. Again, the test vector here is the digits of my student ID, and the second test vector is the double of the first test vector. So in this, the results are stored in a register R3, R5, and the test vector is stored in R6, register R6. The third program that is used to implement is to verify is the factorial of a number, and the factorial of the number chosen is 4. For in this program, a recursive loop is used, that is, the function calls itself to compute the factorial. The result is stored in the register R2. This is how the value of n is stored. In conclusion, finally, the 5-stage pipeline processor, which has a subset of NIOS 2 instructions, is implemented and tested using 3 programs. The results were found to be as per expectations. This is proved by the waveforms. The additional waveforms are in my report. Relation between speed up, and one of the concepts that was understood was the relation between speed up and the number of processors. Uh, Speed up is calculated as Ts by Tp, where Ts is the sequential time, Tp is the parallel time running on p parallel processors. The future scope of this project, had I been given more time, I would have added 4 more instructions. Lengthier programs can also be implemented in subsequent versions. Additional cache memory data forwarding unit also can be added. Thank you.